Okay, hello. My name is Isaac Blanky, and today I will be doing an overview of the side splitter theorem and its corollary theorem. So let's start out with a definition. The side splitter theorem states that if a side of a triangle is parallel to the base and intercepts the two other sides, it splits them proportionally, which means that Cx over Xa will be equal to Cy over Yt, where the triangle pretty much looks as follows. So from this diagram, we can see that this line L, which for some reason was not appearing in previous recordings, so I had to draw it in manually, sorry, is parallel to the base AT of this triangle. And following the side splitter theorem, Cx and Ax are split proportionally, and Cy and Yt are also split proportionally. So Ct and Ca are split proportionally into these two, these four actually, two for each side. So what this creates is basically triangle CXY, which is in total going to be similar to the whole triangle. Firstly, it can be proved through the side or side through the angle theorem for similarity in a triangle, but it can also be proven through the side angle side theorem for similarity, because what happens is if we say that this side length is going to be 5 of this side in total, and this side length, for convenience, let's just make it 10, even though it's not correctly represented in the diagram. We say that this splits it proportionally, so that this is 3 and this is 2. Then this will become by the logic of the theorem, 6 and 4. So because these two sides are have the same 2-to-1 ratio as these sides, and angle C is shared, this triangle can be proven similar to CXY. So that's just an example of how it can be used to prove triangles and also find side lengths, which is probably one of the more important uses of the theorem. But its corollary is also very useful. If you take 3 or more parallel lines, and we take 2 other lines that are not parallel to the original 2, and we use it to cut these lines, then it will cut them proportionally. So we have lines L, X, and Z, and we also have lines A and B that were, actually not parallel to each other, nor this, but they can be parallel to each other for the theorem to still work. So we take this and we look at this segment between these two red dots, And we can, let's for example say that this that the proportion between this part and this part is 1 to 1, which means that these two are going to be congruent. Then, because of this theorem, the proportion will also be 1 to 1, and these two will also be congruent. So this is good for proving congruence. It's also good for finding values, and of course similarity. So let's say we have a line that's right here. The whole thing is going to be going to be 10, and this whole line is going to be 15, and it splits it in a 1-to-1 ratio. For example, you would get this as 5, because we know that the ratio is 1 to 1. This is also 5. And then we take this, and because it's 5 to it's a 1-to-1 ratio, or a 5 to 5 ratio, which simplifies to a 1-to-1 ratio. We take 15 and we set it equal to 2x, which is basically the same thing as dividing it by 2, and we get that this is 7.5 for each. So that's how it can be used to find values. In constructions, it helps us do a pretty important construction, which is trisection. So we make a first line, which we want to trisect, and then we make another line that is not parallel and comes out of the part. It's a ray. It's going to be a ray. And then we take it and we find three points that are 3 line segments on this ray. They're going to be equivalent to each other, and at the end of the third one we connect it back to the end of the line segment here, and we do this with our compass, which is really difficult to do on the laptop. Then we make parallel lines, just like in the theorem 1, 2, 3. And because we know that the side splitter theorem is true, we can say that because it splits these 3 equally, it must also split these 3 line segments equally, and therefore we just trisected it. This can also be done for pretty much any splitting of a line segment into equal parts. We could do the same thing for 5, 6, 7, 8, 9, 10 in construction. And another more real-world use outside of geometry for this theorem is if you're going to do gardening. Most people that do gardening or ever read the back of a seed packet know that most of the time, whether you're doing large farming or just gardening in your backyard, you have to separate your plants by an equal distance, and you want them in rows. So basically what I did here is I made the rectangle, and we're gonna pretend that the rectangle is a plot of soil, and we cut the 3 lines, the 3 parallel lines. So what we're really looking at is that because these 3 lines are parallel, and we take the distance, we want the distance between them to be equal. So we can take this and we make it so that this is a 1-to-1 ratio, that this first plant is going to be a 1-to-1 ratio with this plant and this plant on these 3 parallel lines. then every single plant is going to be on the same ratio, and therefore they'll all be the same distance. And this is actually really necessary for the plants to grow correctly. So that's actually one of the more important uses in the real world for this theorem, outside of architecture and geometry. Thank you for watching. I'm sorry at parts I stuttered trying to figure out the technological work behind this theorem. I will post the PowerPoint in the description link below if for some reason you just feel the need to look at it. Thank you.